So we want to calculate the frequency and energy of blue light that has a wavelength of 400 nanometers. You can do these in whatever order that you want, but since frequency is asked first, I'm going to do frequency. We know that the speed of light c is equal to the product of wavelength and frequency. We know what the wavelength is, and c is a constant. So c divided by the wavelength is equal to the frequency, which is 3 times 10 to the 8th meters per second. Again, that's a constant. Divided by 400 nanometers, that's 4 times 10 to the minus 7 meters. This gives me an answer of 0.75 times 10 to the 15. Now that's hertz, or I could use inverse seconds, one or the other. And to put this in proper scientific notation, that's going to be 7.5 times 10 to the 14 inverse seconds, which is the answer for the first part of number 3. Now we can solve for energy. We could base it on what we just calculated. We could also base it on the given information. My preference is to use E equals HF because it's only one mathematical operation, whereas if I use HC over lambda, it's 2. This will be 6.6260755 times 10 to the minus 34 joules times seconds times 7.5 times 10 to the 14 inverse seconds. Of course, we know that the seconds will cancel, leaving us with joules. So when we simplify this, we get 4.97 times 10 to the minus 19 joules. This is joules per photon, which becomes very important in answering questions 6 and 7 on this worksheet. All right, number 6. We want to calculate the number of photons having a wavelength of 10 micrometers required to produce 1 kjoule of energy. So the first thing I want to do is find energy per photon. E equals hc over lambda. And just in terms of strategy, I'm going to have the total energy. I will divide that by the energy per photon, and this will give me the number of photons. That's the strategy. So hc over lambda, we know h is 6.63 times 10 to the minus 34 joules times seconds times 3 times 10 to the 8 meters per second divided by 10 times 10 to the minus 6 meters. We can start canceling out units. Meters cancels. Seconds cancels. This will be joules per photon. So 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 10 times 10 to the minus 6. I get an answer of E equals 1.99 times 10 to the minus 20 joules per photon. The total energy I have is 1 kjoule. That's the same as 1,000 joules. I'm going to divide that by 1.99 times 10 to the minus 20 joules per photon. Joules will cancel, and photon, it's part of a complex fraction, will become my numerator, and I want number of photons. So now I just need to simplify this expression, and I find that the answer is 5.03 times 10 to the 22 photons. Here we go. Number 7, I'm going to calculate the total energy in a certain number of photons having a wavelength of 3.0 times 10 to the minus 12 meters. So the strategy for this is we're going to find the energy per photon and then multiply it by the number of photons. So let's go green for show me the money. E equals hc over lambda times the number of photons. So that's going to be 6.63 times 10 to the minus 34 joules times seconds times 3 times 10 to the 8th meters per second divided by 3 times 10 to the minus 12 meters. And then I'm going to multiply this by 1.5 times 10 to the 13 photons. Of course, this is divided by photons. Photons cancel, and seconds cancel, and meters cancel. So now it's just a plug and chug. .63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 3 times 10 to the minus 12 times 1.5 times 10 to the 13.
Would the following scholars please see Ms. Beecham at the front desk after dismissal?
0.995 joules
Taylor Johnson
is the total energy.
All scholars